Welcome to Brain Vision.
Okay, so in this question, we have a string that is bound at both ends, and the length of the string is equal to 2.00 meters. Its mass is equal to 0.100 kilograms, and the tension in the string is held at 20.0 newtons. And from this information, we're supposed to figure out what the fundamental frequency is, as well as the second and third mode of vibrations and what those frequencies are. So we want to figure out the three lowest vibrations that this string can have. So the way that we do this, first of all, we just start with saying that the frequency is going to be equal to the speed of the wave divided by the wavelength. Now, since the wave is, since the string is bound at both ends, we're going to have nodes at either end, which means that for the fundamental, which is what we're looking for here, we're going to have nodes at either end, which means that the wavelength is going to be twice the length of the string, because you'll go from one node to another node, but that's only had one antinode in the middle. So in order to get the full wavelength, you have to go to the opposite antinode and then back to another node, which would take twice the length of the string. So we have that lambda is going to be equal to 2L. And then for strings like this, the speed of the wave is going to be equal to the square root of the tension divided by mu. And of course, mu, I'll put this a little further over. Mu is just equal to the mass of the string divided by its length. So if we plug that into our square root, we can then rewrite the formula for V as T times L over M. Because you flip M over L, and so L ends up in the numerator and M is in the denominator. So we have formulas for, so our formula for F1 is V over lambda, and we have formulas for lambda and V that use only the variables that we know, so we can go ahead and figure out what our fundamental frequency is. So F1 is going to be equal to, if we plug in our formulas for V and lambda, it's going to be equal to the square root of T times L over M divided by 2L. So now, if we go ahead and plug in the values for those, we have the square root of tension is 20.0 newtons times 2.00 meters. That is divided by the mass, which is 0.100. And all of that is divided by 2 times 2.00 meters. And if you calculate that out, you should get that the fundamental frequency of this string is 5 hertz. Now, of course, we need to figure out what the next two modes of vibration are as well. So we need to figure out F2 and F3. Well, F2 and F3 are simply going to have frequencies that are just integer multiples of the fundamental. So F2 is going to be 2 times 5 hertz, and F3 is going to be 3 times 5 hertz. So F2 is going to be equal to 10 hertz, and F3 is going to be equal to 15 hertz. So our answers for part A are 5 hertz, 10 hertz, and 15. Having trouble writing today. There we go, 15 hertz. And that's our answer for part A. And then in part B, we're told that we're seeing a node 0.400 meters away from the end of the string. So with that information, we're supposed to figure out what mode of vibration the string is in and what frequency it's vibrating at. So what Well, if we compare 0.400 to the total length of the string, we'll see that that is 1/5 of the way along the string, which kind of indicates for us that it would be the fifth mode of vibration. Because if it was in the second mode of vibration, we'd have a node halfway, and then halfway through the string, and then nowhere else. We'd have, for the third mode of vibration, we'd have two nodes, each a third of the way through the string. The fourth node, we'd have one every quarter of the way through the string. And for the fifth node, we'd have one every fifth of the way through the string. So that tells us that this is the fifth mode of vibration. And since it's the fifth mode of vibration, we can just do what we did in part A and multiply the fundamental by an integer to figure out the frequency that we're dealing with. This time, since it's the fifth mode, the integer is 5, and 5 times 5 hertz, obviously, is going to be 25 hertz. So that is our answers for part B, and we are all done with this problem.